Okay, um, number 4, geosynchronous satellites. So what is a geosynchronous satellite? Well, it's most satellites, most of our communication satellites for your cell phone, your cable, whatever, satellite, not cable, but whatever, they travel around and they stay above the same spot on Earth all the time, right? So they actually then have a period of 24 hours, right? They get to a certain distance from the center of the Earth and they travel around and they follow, for example, us. There might be a satellite directly above us and it always follows us. So its period's 24 hours. And that's geosynchronous, so it works with us. And like I say, most communication satellites, excuse me, that's the truth. That's how they work. So just looking at a few questions related to geosynchronous satellites. The first one is saying there's a 500 kilogram satellite. We want to place it into geosynchronous orbit. And how high up does it have to go? That's the first part. And the way that you figure that out, is really you just make centripetal force equal to gravity force, knowing given the period. And you solve for the radius. This will lead, if you haven't thought this through yet, you will see this will lead to a common answer. All geosynchronous satellites orbit at the same radius. And we'll see, because mass is going to cancel. Gravity, centripetal, they both have mass in them. They're both going to cancel. This 500 means nothing. Okay, but let's go through the process and solve. Fc equals Fg. I chose the formula for Fc that has period in it. So this is just one of the circular motion formulas, right? Mass times 4 pi squared r over the period squared, because we're given the period. 24 hours, by the way, it's 8,600 seconds. It's just, you multiply 24 hours times 3,600 seconds in an hour. And those cross out, and you end up with the number of seconds in a day. So that's the number of seconds in a day. Sub in the mass of the Earth, because the mass of the satellite cancels, like I said. And you end up having to take the cubed root. So depending on how you do it, when I put it in my calculator, I put all this in with the numbers, and then I went exponent 1 over 3, or your calculator might have a cube root button, whatever, but you have to find the cube root, and you get 4.2 times 10 to the 8, which, I could just Google that. Let's see if it's a reasonable answer. What is, and you'll see that I've done this before, by the way, what is the radius of geosynchronous orbit? And blah, blah, blah. Here it is a geosynchronous orbit with the plane, 42,000 kilometers, which should be 4.2 times 10 to the 5 kilometers. Looking at our answer, it's in meters, and it's 1,000 times 1 meters, so it makes perfect sense. So our number is definitely a good one. Okay? So that's finding a geosynchronous orbit. That's finding the radius. The next part, same question. Now we want to find the gravitational potential energy of that satellite before it's launched. So it's just sitting on the surface of the Earth. So the information we know is the mass of the Earth, we know the radius of the Earth, and we know the mass of the satellite. And so the strategy we'll follow is just to use the GPE formula, the general formula. You might say, well, why, if it's on the surface of the Earth, how come I can't just use the MGH? Well, the problem, of course, with that is what is H, right? I guess you could use H and have H be the center of the Earth, the radius of the Earth. You could do that, actually. But anyway, this is the form that I used. And the idea is that it's a negative number, okay? Which, again, has no meaning for us. And I'm not even going to check mark this, because this is a crazy number. We can't picture it. I can't Google this one, okay? So I'm just going to leave it alone. Eventually, this number will have some meaning, but right now I can't check mark that. Okay? So that's how you solve for the gravitational potential sitting on the surface of the Earth. Okay? Moving on. Same problem. Now I want to know the total energy, which will be the sum of kinetic and gravitational, when it's in orbit. So the information that we need then, we need the radius of the orbit, which we figured out already. We know the mass and we know the period. But we don't know, for kinetic energy, we still need the speed. However, something we can do, knowing the circumference of the motion, and we can do that, 2 pi r, right? That's the distance, and then the time is the period, right? So it takes 8,624 hours, whatever, 86,400 seconds to travel one full circumference. So you can use speed, find speed using that. Okay? So you can see when we do the solution here, that's the first thing I did. Found speed, so it's 3,000 meters per second this thing is moving around at that high elevation. So again, I use that for R, that for T, and that for M. And then I need the total energy, so EK, 1/2 mv squared. So again, I get some giant number that means nothing to me. EG is another giant number that means nothing to me. And I get an EK, a third giant number that means nothing to me. Okay, so here again, all I know for sure is E total, is a negative number. And that means nothing to me. Seems weird that it'd be negative, right? But let's just keep going and we'll see why negatives sort of help physicists do math, help us do rocket science. Continuing with the same problem. Oh, this first one's actually just saying how much work do you have to do to place it into orbit? Okay, well, work is the change in energy. So it's the energy in orbit, which we just calculated. Subtract the energy that we calculated at the beginning, which is the original energy of it just sitting on the surface of Earth. Okay, so that's actually not very hard. So let's say how much work do you have to do? That's how much energy do you have to add, right? So you go through, I guess that'd be an ET2, not just ET. There we go. So that's the total energy in orbit. That was the one we calculated at the very beginning when it's sitting on the surface of the Earth. And it ends up being a positive number, which makes sense, right? Because you have to add work. You have to do work to get it up there, right? So the negative in that context, it's a good thing, right? Because if it wasn't negative, then this whole thing would be negative. It would be saying you have to do negative work. And that wouldn't make sense. Why would you have to do negative work if you got to push this satellite up into space? Okay, so it means a little bit. And that's the only, as far as this number, is it a good answer? Well, it's positive. If it was negative, I'd have to say, why would you do negative work in this case, right? So the only thing I'm really check marking there is that I got a positive answer. These numbers are so crazy and out there that it's hard to know. Continuing with the geosynchronous orbit, here's the interesting question. How much more energy do I put in to get it outside of our potential well? And again, that's the idea of having no energy at the end. And that again, it makes kind of sense that it's negative because we need to have no kinetic energy and no gravitational up there. So it's got to be zero. Well, another term for that, by the way, is binding energy. So we got to take the zero and subtract the energy while in orbit. And the energy while in orbit, we figured out was a negative number. Right? So energy required to escape Earth's potential well is just enough to have a total energy of zero. We got to add a bit more energy. This satellite, it's going around Earth at 3,000 meters per second. It's got what we call a negative energy at this point because of the gravitational. And if we want to get it out, say we want to somehow, I don't know, through solar panels or something, just get it out of our potential well. We want it out of here. We need to add this much energy to the system. Okay? And so it's like it's sitting at a negative. We want it to get to zero, or like we want it to leave and not just hang out, but leave and go, keep going and never come back. Just add like 4.6 or 4.51 times 10 to the 9 joules. Okay? Okay. Just looking at binding energy then, I use the term, it's the amount of energy, again, that you need that you need to escape Earth's potential well, to get out of our gravitational field. And the truth is A and B are the same question. That's just two different ways I could word the same question. I just scratched out C because it's not that relevant, okay? But A and B are the same question, so it should go quick. Binding energy is the energy required to leave Earth's potential well. And so this person, we're assuming, is sitting at rest at Earth, so the only energy they have at that moment is their EG, right? So you just it's a negative number, negative 4.1 times 10 to the 9. So the answer then, if you want some 65 kilogram person out of Earth's gravitational field, you want them gone forever, you've got to give them this much energy. In the form of kinetic energy, by the way. And they'll be gone. They'll be out of here. Okay? In part B, it's just another way of saying the same thing. Okay? So that's just A and B, same question. If you need to pause and write that down, please go ahead. All right, one more short video after this.